We got a lot to cover today. We are going to talk first about modeling functions or modeling data using quadratic functions. We're going to talk briefly about projectile motion. I know you're taking physics, and I'm sure you have done.
Disregard the fact that I'm taking physics.
Say that again.
I said you can basically just disregard the fact that I'm taking physics.
Okay. So we're gonna talk about how to model projectile motion with quadratic functions, and hopefully the way that I'm gonna present it make some sense. Hopefully, and we'll see. If not, well, we'll come back to it. And finally, this is my favorite thing. This is one of my favorite things in mathematics. Is we're going to do some optimization problems. Optimization is like, by that we mean we're finding a maximum or a minimum value of something. Like, well, you'll see. And so those are the big three for today, and we're going to try to get through all of it. So let's start with modeling data with quadratic functions. But before we even think about quadratic functions, we have data right here, and we want to use a function to model this bad boy. And right now, all we have are just two columns of data. And what we're looking for is an input and output relationship between one of these columns with the other columns. And the first question we have to ask is, what's the input and what's the output? Now, usually canonically, what they do is the left-hand column is your input, the right-hand column is your output. Sometimes, and usually, hopefully, it's stated like, we want a function which takes this as input and that as output, and blah, 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 blah. But let's say that we didn't know which was my input and which was my output. It turns out that that one way of thinking about this will be possible. The other way will be completely impossible. So what we're going to do, and this is whenever you want to model data, the first step is always going to be graph the data. Okay. So what I was saying here is we have a choice. We're not sure which is inputs and which are outputs. So let's just assume right now that the first column are inputs, the second column are outputs, and let's go ahead and just graph. Okay, if the left-hand column are inputs, then we have something here at -1. Okay, so I'm going to do the first point. It says that when I plug in a -1, I get out a +1. So all I'm doing is just graphing points. Okay, so that's my first.
Should I be copying this down?
You better be.
Okay.
You better be.
I was.
I say not to. You better be writing everything down.
Okay.
So, okay. But good question. Thank you for asking.
Just checking.
Okay, so input is -1, output is 1. Okay, this says when my input is +1, my output is 3. This says when my input is +2, my output is 1. Okay, so this is, we weren't sure which was my inputs and which were my outputs, and this was my first assumption. The other option is that we just switch the roles of inputs and outputs. So we say, okay, what if these are my outputs and these are my inputs? Let me know when you've caught up, when you have all this written down. Okay. So now we're going to switch the roles and we're going to say, well, what if the right-hand column were my inputs? Okay, well, this says that I plug in a 1 and I get out a -1. Okay, so I'm down here at this point, 1, comma, -1, right? That's the first data point. The second data point says I plug in a 3, I get out a 1. Okay, so I plug in a 3, I get out a +1. There's my second point. The third point says I plug in a 1 and I get out a 2. So I'm at this point. One of these defines a function. The other one of these does not define a function. Which one of these cannot be a function and why?
Hold on, I'm gonna finish graphing.
Okay. This was like one of our first things we did in class. So we gotta think back a ways. If you're not 100% sure, a function has to pass a certain test, or the graph of a function has to pass a certain test.
Right. Hold on. Hold on. 1. There. 1, 2, 2, 1, and 1, 2, 3, 1. Okay, there we go. Okay. The second one is not a function.
Why?
It doesn't pass the line test.
The what line test?
The vertical line test?
The vertical line test. Yes. Okay. And what does that mean? Well, remember from the definition of a function has to have, for every one input, it gives you one and only one output, right? And
Right.
the vertical line test is a fancy way of talking about the graph. What this says, this right here, if this were a function, it would say that when I plug in a 1, I get out, what, 2 numbers? How could that be? I get both a 2 and a -1 as an output. That's not a function. That is something else. That is something completely different. And if you tried to find a function which does this, you would be trying for the rest of your life and you would never find one. So it's a fool's errand, right? And it's just it. So the takeaway point here is whenever you're given a table of data, usually you know what the inputs are and you know what the outputs are. But if you didn't, right, and it may not be the case that you actually run into this, right? If I had just changed this one number, maybe if I'd made that a 2, well, then it would be ambiguous and you could go either way. But in this case, we happen to have a data set which absolutely, if you interpret it this way, where these are inputs and those are outputs, then it is impossible to find a function with this property. So step 1, whenever we're dealing with modeling data using a function, is going to be graph the data. Mm-hmm. And that will help prevent us from making a mistake like, confusing the inputs and the outputs. It might not, but if there is a huge contradiction in the data, like we just saw, then it's going to come out when you graph the data. So at any rate, now we know what the inputs are and the outputs are. In your homework, it will be obvious what the inputs are and what the outputs are. And so that's not really the reason that we're going to still do step 1 is not to find what the inputs and the outputs are, but this is really good practice to do. Okay. So that's step 1, graph the data. We always want to do that. Now, step 2 is going to be write the general function that you're looking for. This is very similar to when we were plotting lines. And my first step, I said, write down somewhere on your paper, y equals mx plus b. And then we're going to go and solve for m, and then we're going to go solve for b. But it's so important to have this somewhere on your page. And so the idea is the same here. We want to write down the general form of the function that we're using. So now what we're going to do, and in your homework, we're going to be using quadratic functions or quadratic functions to model the given data. And so I'm going to say, well, a general quadratic function is, well, we've seen this 1,000 times, ax squared plus bx plus c. If I were so inclined, I could say, well, what about ax minus h squared plus k? We could do that. That's possible. We'll see in a minute that this way is going to be way nicer for what we've been doing. Now, let's just, as an aside, I've said this a few times. I'm going to say it again. Right now, we have, so in the case where we had y equals mx plus b, we had two unknowns, right? That our goal was to find those two unknowns, right? Our goal was to find some value of m and some value of b. And in order to solve for two unknowns, we needed two equations. Or if we're thinking about points, we needed 2 points to do that. The same thing is true when we have 3 unknowns. Right now, we're trying to find a value of a value of b, and a value of c, so that when I plug in a -1, I get out a +1. When I plug in a +1, I get out a +3. And when I plug in a 2, I get out a 1. And it turns out that we are going to need 3 equations to solve for this guy. That's just in general. Anytime you have 3 unknowns, you need 3 equations to determine those. Now you might, right here, you might say, wait a second, Justin. This last homework that I did, we had 3 unknowns. We had A, H, and K. And you only gave me 2 points. You're telling me I need 3 points in order to solve these, but I just did a homework where you only gave me 2 points. But this is the trick here, is in the homework, I told you that one of those points was the vertex, right? If I said the vertex is at 1, 2, you would know, okay, wait a second. That means that this H right here is the 1 and the K here is 2. So this is a very special kind of point. That's if we know that this thing is a vertex. In this case, we have no idea if any of those are vertices or not. Like, it kind of looks like the 3 up here, the 1, 3 might be a vertex, but we're not sure about that. What I'm saying is, in this last homework, essentially what I did is I did give you 3 equations. I said, okay, if this is the vertex, then essentially I've given you 2 equations. One of them is H equals 1. The other one is K equals 2. And then finally, I gave you some kind of point. I said, okay, you have, like, say, it goes through at -1 and 2. And so the third equation was f of -1 equals 2. And so in the last homework, you were working with 3 equations. You just didn't know that this guy actually contained 2 equations. In this case, we have no idea whether this bad boy is a vertex or not. And so we can't just take that and plug it in, because, well, this thing might shoot up like this and come back down. The vertex might not be there. Or it might actually be the vertex, I'm not sure. Or it could overshoot here and come back down. It could do a lot of things. But in this case, this is about as general as it gets. We have 3 points. We have 3 unknowns. And so what we're going to do is use those 3 points to get 3 equations. Okay, so we've graphed the data. we've written the general function. The thing that I'm trying to model here is a parabola. What does a parabola look like? Well, it's ax squared plus bx plus c. Cool. Now, my data says that when I plug in a -1, I get a -1 squared plus b times -1 plus c. It says that the output is a +1. So here I'm using 3 points to get 3 equations. There's my first equation. I'm going to use my second point where I plug in a 1. That gives me a times 1 squared plus b times 1 plus c equals +3. Okay. Finally, when I plug in a 2, I get out a 1. And so I plug in a 2. What does that do? Well, it says 2 goes in here and gets squared. I put a 2 in right there. And the output of all of that is a +1. Cleaning this up, a times 1 squared is just a. B comes out to -b, and then plus c equals 1. This is easy. A plus b plus c equals 3. Finally, a times 2 squared is 4a. B times 2 is 2b, and c gives me a 1. Now, okay, we got 3. We used our 3 points to get 3 equations. We have 3 equations, so we're going to use a matrix to solve for my unknowns. To solve for unknowns. Okay, so that is, and I'll do it right here, give myself room. 1 minus 1, 1, 1. 1, 1, 1, 3. 4, 2, 1, 1. Okay, that is that. I'm going to double check that. 1, -1, 1, 1. 1, 1, 1, 3. 4, 2, 1, 1. All right. I'm going to take that and subtract. I'm not changing the top row. Subtracting gives me a 0. That subtracting that gives me a whole +2. Maybe that's what happened. Subtracting gives me a 0. Subtracting gives me a 2. I see where we went wrong. Aha, we didn't get that last time. Okay, now -4 times the top is -4 plus 4. -4, -4. I take that and add that to the bottom row to get 0, 6, -3, and -3. Oh man, I feel good about this. Now let's go ahead and knock these guys down to 1s. -1. 1, -1, 1, 1, 0, 1, 0, 1, 0, 1, -½ -1/2. Now, I'm going to take this guy and subtract off to give me, not changing the top, 1 minus 1, 1, 1, 0, 1, 0, 1. That's nice. Subtracting gives me a 0. Now I'm not subtracting anything off of there. Now I take a 1 and subtract it, and that gives me a -3/2. Right there. Okay, just make sure I did that right. I subtracted. I took 1, subtracted. Yep. Took that, subtracted, didn't do anything. I took -1/2 and I subtracted 1, which is the same thing as subtracting 2 halves to give me -3/2. Yes. But I could take that and multiply that row by 2. Then I could take that and multiply that row by -1 to give me 1 and 3. I'm going to take this and subtract it off of there. This guy is not changing. This guy is not changing. Taking that and subtracting gives me a 0. 1 minus 3 is minus 2. Okay, buddy. Finally, we add that to that, and that should kill that last one right there. This guy is not changing. This guy is not changing. I take that, oops, that and add it to that. That stays put. That becomes 0, 0, 0, 0. And we get a minus 1, just like I knew it had to be. Okay? Yes. So what does this say? Well, remember, this says A plus 0B plus 0C equals -1. This says that 0A plus 1B plus 0C is equal to 1. And this says 0A's and 0B's plus 1C is equal to 3. So this now brings us to our second to last step. So I've solved for this. So now we've solved for the unknowns. And so now we are going to write the function. Because you're not done. If I asked you to do this to find a function and you stopped right here, I'd be like, you didn't tell me anything. Like you told me what A, B, and C are, and yes, technically, yeah. But let's put it all together, right? If your boss says, give me a function, they're not asking for this and this. They want to see the actual function. So let's write that actual function down. That is f of x. Now, a is -1, so I'm going to write that as minus x squared. B is +1, so I'm just going to write that as plus x. Finally, C is a +3, so I'm going to write that as a +3. That's my function. Step 6, you could guess what this is. Check it. So let's check our work. Okay, it should be the case. This function should satisfy this input-output relationship. It should be the case that when I plug in a -1, I get out a 1. When I plug in a 1, I get out a 3. When I plug in a 2, I get out a 1. So let's make sure that that's the case. F of -1 equals -1 squared plus -1 plus 3. Making sure, just looking again to see, like, did I do this right? Yes. Okay. It's going to be negative something squared. And so it's going to look like that. The negative is going to go in there. Okay. So -1 squared is +1. So that's -1 minus 1 plus 3. That's the same as -2 plus 3 is +1. I plug in a -1. I get out a +1. That point checks. We're good to go. Okay, we're going to do it now with 1. Plug in a 1, and I get -1 squared plus 1 plus 3. -1 squared is 1, okay? Plus 1 plus 3. The 1 and the -1 are gone, and I'm just left with 3. Good, check. Finally, it says that when I plug in a 2, I should get out a 1. So let's see, -2 squared plus 2 plus 3. I get a -2 squared is 4 plus 2 plus 3. -4 plus 2 is -2 plus 3. Gives me a +1. And so all of these points check. We are good to go. I'm so embarrassed with that big mess up. It's what I get. I shouldn't have said, I'm going to do this really fast. I should have just, that probably messed with my brain right there. But it finally worked. Okay. But actually, it may have been good because then you could see some reasoning there. I knew before I even finished that, and not just because I had done it before and I knew what values I was expecting. I couldn't remember that it was -1 1 and 3. That wasn't in my head. But what I knew is that this thing has to be a downward facing cup, right? Like, look at it. If the parabola fits that, it can't be upward facing, right? And so when I started seeing that my A was going to be a positive number, that didn't make any sense, because as we've seen 100 times, every one of these things that we've done, whenever A is positive, that's an upward facing cup. And we could reason that through by looking at this kind of thing right there, right? Every one of these can be written like this. That means you shift the upward facing cup right or left. And if A is a positive number, he stays upward facing. And so you can't have a positive A and have a downward facing cup. In fact, they are the same thing. If it's a negative, if A is negative, it's a downward facing cup. If A is positive, it's an upward facing cup. So I knew that something wasn't right. And so, okay, at any rate, this is it. This is what we're looking for right there. Now, an interesting thing to do, and since we're not going to get to our last topic, we might as well go ahead and just do this. Right now, I could ask, okay, like maybe this relationship was given and it said this is how many widgets I produce, and this is how much revenue my company gets when producing that many widgets. So it says, what's a negative widget? Don't read too much into this. It says, like, you know, if I produce one widget, I get $3. If I produce, or maybe it's like millions of widgets. If I produce 1 million widgets, then I get $3 billion. If I produce 2 million widgets, though, I only get $1 billion because they're, you know, it costs too much to make widgets. So how many widgets should I make? If I want to optimize the number of widgets that I make, well, what we're looking for then is the biggest amount, right? We're looking for the highest point on this parabola. So if we want to then Kayla's there. We can't see Kayla though. Sorry. So what we're looking for is the vertex. And we could say, okay, and we'll go way into this. But when we go to actually talk about optimization, which is one of my favorite things. But we could say, okay, the output of this function, we want to know when is it at its highest? Well, it's a parabola. And so it's at its highest at the vertex. That's its very biggest output value that it could possibly have. And we know that the vertex always occurs in terms of B and A. Where does this thing always occur?
B over 2A or minus B over 2A?
Minus B over 2A. There you go, right? So it's like, well, let's see where that is. We know that we actually had it written down. The A was -1 and the B was +1. And so let's see. The vertex of this guy, I'm going to call it x sub v for the vertex value of x, is -b over 2a. And that's a is 1, b is 1, so that's -1 over 2 times -1. Negative over negative is a positive. And so the x value is 1/2. So if the question was, how many widgets input should I produce in order to get my company the most money, we'd say, well, 1/2 or 500,000 or whatever, right? We would be able to say that the max value occurs when x is equal to 1/2. In other words, the vertex is here at 1/2. Kind of like how I've drawn it right here. So this thing must come up, go up here to 1/2, and then down through those points right there. That's what that guy looks like. And then we could say, well, then what is that value? I'll plug it in and find the output value. Let's see, f of 1/2. It had, whatever I get had better be bigger than 3. Otherwise, all of this is lying to me. but let's just see. Plugging that in, I get a negative 1/2 squared plus 1/2 plus 3. Negative 1/2 squared is 1/4 plus 1/2 plus 3, but I'm going to write 1/2 in a way that makes sense to this problem. How about 2/4? So that minus 1/4 plus 2/4 is plus 1/4 plus 3. And so, I mean, I don't need to actually do that. I could just see, okay, 3 plus 1/4. Yeah, that's what it would be. You would have 3 plus $250 million. So 3.25 billion would be how much money my company could make if the output were in billions and the input were in millions of widgets. So I would tell my boss, hey, if you want to maximize our revenue, go and produce 500,000 widgets right here, 1/2 million widgets. And we can expect that our revenue will be 3.25 or $3.25 billion if we produce 500,000 widgets.
Okay.
So that's the idea with optimization. We'll go into that. Like there's there's going to be, again, I'm going to give you steps and stuff for optimization problems, but I just wanted to kind of tack that on to the end of this because, well, we have a nice parabola, and with any time I see a parabola, I always wonder how high does that thing go, or if it's an upward facing parabola, how low does that thing go? And I'm trying to work this into an actual word problem type that you're going to see. But this is the idea. If you have a function, you could find, and if you have a function, a parabola, that has a highest value, you could find that highest value. And maybe it's something that you'd want to know. And you could find out when, and whenever I say when, I'm talking about for what input value that such and such happens. So okay, man, that was so dirty. Oh, man, I feel so bad about that. We could, okay, anyway, I'm not going to beat myself up. Does all of the, so forgetting about the optimization, that was just something that I tacked onto there. We're not going to have to worry about optimization yet, but you can kind of see that it's coming, especially since we spent so much time talking about how to find a vertex. Aside from the optimization part, how do you feel about all of this?
Fine.
Okay. Now, I just want to say, this works regardless of what type of thing you're doing right here. I happen to say use 3 points to get 3 equations, but if we happen to have more data points, let's say I had a 3 and a -2 and a 5 and a 6 or something like that. Well, we have 1, 2, 3, 4, 5 points. We could have a function with 5 unknowns. And what might that look like? Well, how about something like this? Ax to the 4th plus bx cubed plus cx squared plus dx plus e. Given 5 points, we can solve for 1, 2, 3, 4, 5 unknowns. I'm not going to ask you to do this because that would be a wicked hard matrix to do, right? You'd have a 5 by 5. We're not going to worry about that. But this is exactly what you would do. In fact, when I was teaching beginning scientific computing at UW, it's AMath, Applied Math 301. That's what it was then. I'm not sure what it is now. But this is exactly what we do. We just do it with a computer. And you say, okay, given these 3 points, find a polynomial that fits this data. And it turns out that as long as you have unique inputs, right? Like we were talking about before, you don't have one input and 2 different outputs. As long as you have different inputs, doesn't matter if the outputs are the same or what, you could always find a polynomial that goes through each one of these points. The way you do it is exactly the same as this. You'd start by graphing your data. Then you'd say, okay, this is the general function I'm looking for. And then instead of using 3 points to get 3 equations, you would use 5 points to get 5 equations. You would start off by saying, well, okay, f of -1 equals, you plug in a -1 and you say, okay, well, that the output's 1. And you do that all the way down to you plug in a 5 and you plug in a 5 and you get all this stuff. And finally, the output is 6. Well, that's a big matrix. And you just plug that into a computer solves it for you. And then you have your function that does all this stuff. So, okay. We good to move on?
Yeah.
Okay, so. All right. Okay, 11:30, and it's not too bad. So, projectile motion. Oh man. So, one of the biggest problems is when people think, like, let's say my phenomenon that I'm trying to write a function for or analyze using a function is that we're throwing a ball up in the air. And your teacher says, well, this can be done with a parabola and stuff like this. And they go through how there's this function, blah, 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 and it has this form right here. And yeah, and we know because there's this graph and stuff like this. The problem people have is in their mind, they have this idea that the ball is moving along this trajectory. The ball is not moving along this trajectory. This is not what's happening. When we're talking about a ball being thrown into the air, and saying like, and there's a parabola that describes it, it's not that the ball is moving through space like this, that it's moving up and over and then coming back down. And this somehow, this thing here gives you the position of the ball. That is not what's going on at all. What's going on is this. So this is a time axis. Our input axis is going to be time. It has nothing to do with space. Nobody's moving in this direction. We're not moving in this direction at all. We're only moving in one direction. And that's going to be straight up. And what I'm going to do is draw a stick figure. In case you haven't been able to tell, I love my stick figures. This stick figure has a ball in his hand. There's the ball in his hand. And when we begin this experiment, we're going to start our clock, and our clock is going to be at 0. And what we're going to imagine is that there's a big, that this is a wall, that what I've drawn right here is an actual wall in the real physical world. And so it has an actual height, right? And there's a ground level, and that ground level is what we call 0. It has 0 height right there. And it's a wall that just goes up, literally up in space. And what I like to imagine is that there's a big spotlight right here, or a big flashlight. And it's shining light in this direction onto the wall. And so this is the experiment. The person's going to take that ball and throw it straight up, not over like this in this direction. There's no sideways motion. We're taking a ball. Oh, nice. We're taking a ball, we're going to throw it straight up, and it's going to come straight back down. There is no sideways motion going on at all. It's going to go straight up, it's going to stop, and it's going to come right back down. I think you have a pretty good sense of that because you've probably been throwing things since you were his age. So you're going to throw it straight up, it's going to come straight back down. Now, what we're going to do is we're going to start our clock at time 0 as soon as that ball is thrown. And what we're going to do is we're going to keep a record of where the shadow on the wall is. So at time 0, when it's in his hand, right the instant that he lets it go, and the light is shining onto the wall, the shadow is cast right here. That's where the shadow is. Now, what I'm doing is on my piece of paper, and we're going to imagine that this is my piece of paper. It's an exact copy of this right here. And I'm sitting here watching this happen with my piece of paper. I've drawn my little axis on it and stuff like that. And what I'm going to do is I'm going to observe where the shadow on the wall is. And I'm also going to be looking at my stopwatch. There's my stopwatch. It's clicking and going. And what I'm going to do is I'm just going to look every second that goes by. I'm going to just note where that shadow is on the wall. Mm-hmm. So when I click the thing, I look and I see the shadow and it's right there. And we're going to say that it's 1 meter off the ground. And so on my paper, I make a little dot right there and I write a little 1 next to it. So now we're seeing what I'm writing on my paper right here. Because the light is casting the shadow right there at 1 meter. Okay, and so then by the time I'm done writing that, I look back and the ball has traveled up, because remember, it's just going straight up. It's not moving in any direction. It's going straight up. And after 1 second, it's at this height. And what I see is the shadow being cast on the wall, and it lands right here. That's where the shadow of the ball is. So what I do is that I look at my stopwatch and it says that 1 second has gone by. And so what I do is I just say, okay, after 1 second, now the height of the ball is right here. And I put another little dot because I'm just keeping track of how high the ball is. You'll notice the ball is not moving in this direction. This is just my abstract record of where the ball is, but I'm taking time into account. Okay, so that's what's going on. Now, by the time I'm done drawing that, I've drawn my second little point and I've labeled it with however high it was. I mean, I guess we could call it 2. We'll say it went up 1 meter in that time. Okay. Now, okay, by the time I've done that, I look, and by that time, the ball has moved, but it hasn't moved as far because it's actually slowing down, right? And like, I'm going to do this, and it's really hard to see what just happened there. But in the first instant, it's going fast, but it's slowing down, right? So like the first second, it's going real fast, but then it slows down and it slows until it comes to a stop. And then it starts moving down, and it's moving slow, but it's going to move faster and faster as it goes down. Mm-hmm. If you took this video that you're watching and slowed it down, you would see that, yeah, in the first second, it covers some distance, but in the second second, it doesn't cover as much distance. That's what's happening. It's slowing down. And so I look up and I see that the shadow on the wall is right there. And so I look at my clock and I see that, okay, 1 more second has gone by. We're here at 2 seconds. And now I just mark, okay, after 2 seconds, the shadow on the wall is now up here. And so I put a little dot. And by the time I'm done doing that, and I put my third little dot on my paper, I look back up, and during that time, this guy has been going, but he's not going as much. And so he ends up right here. And I look at the shadow on the wall. The shadow on the wall is right there. And so I say, oh, okay, I'm going to put, and I look at my watch and I see, oh, 3 seconds have gone by. And so I mark 3 seconds. And I see the shadow on the wall is right there. And so I've marked that right there. Well, by the time I've done that, it just turned out that this thing had gone up and it reached its highest point, and now it's starting to come back down. And that's what we're seeing. So when I look back up, I see that in that amount of time, the ball has come back down and now is right here. And I'm really sorry, like what I'm drawing is that the ball's going up and then it's moving and you're like, you said it wasn't moving left and right, and it's not. I'm just trying to give us some space here. The ball went straight up and it came straight back down, but that's kind of hard to draw on itself and stuff like that. And so, okay. The ball has come down. So what do? Well, I look at where the shadow is, and the shadow has projected it right onto there, say. And so I say, oh, I look at my watch and I say 4 seconds have gone by. 4 right there. 4 seconds have gone by, and after 4 seconds have gone by, the shadow is right there. By the time I'm done doing that, the ball has come down even more. And the ball is here now, let's say, and I see that, oh, the shadow on the wall is right there. And so I look at my watch and it says 5 seconds. And so I go, okay, at 5 seconds, the shadow on the ball is right there. And then I look again after 6 seconds, the shadow on the wall, because the ball has come back down even further, it's right there. So 6 seconds have gone by. Finally, he doesn't catch the ball. It keeps going down. It's been going down. And we'll say after a total of 7 seconds, we'll just say, at 7 seconds, the ball hits the ground and the flashlight casts its shadow right there at 0. And so I say, there it is. Boom. And this is what we mean by projectile motion has this parabolic shape. It's not that the ball is actually moving in a parabola. It's that the height of the ball goes up real fast and then it slows down to a stop. And then it starts to come down. It goes faster and faster and faster until it hits the ground. And if you were to mark these data points, then we're talking purely experimental, no theory going on here at all. If I was really good at doing this and I watched and was able to make this, what we would find just empirically, just data driven here, we would look at this and go, man, you know what? This looks a lot like a parabola. This really looks like a parabola. Maybe it's not, it might not be exactly, but you could do really good experiments and find like, no, it's a parabola. It's very interesting that's a parabola. And you could take 3 of these data points and plug them in to a general function and say, well, you know what? Oh, and wait, my input value is t. So we're not thinking about x here. If my input value is t, you could say, okay, well, maybe this is a parabola. Maybe this is an at squared plus bt plus c. And what you'll find is if you do this experiment about 1,000 times, this a always comes out to be about the same thing. Very, very close to the same thing almost every time. And if you take a physics lab, this is one of the first things you do, is you literally take a video of a ball going up and coming down, and you mark these data points, and you derive what value that is. And after doing this a bunch of times, you see that you get the same value pretty much every single time. And that value is, if you're working in meters and seconds, you find that it's minus 4.9. It turns out that the acceleration due to gravity is 9.8 meters per second squared. And this is 1/2 of that value. When you take calculus, you will see how you could start with this right here and find that, well, if acceleration is 9.8 meters per second squared, it must be the case that that guy is a negative 4.9. Another thing to notice is, why would that be negative? Well, this is kind of like the same thing I did when I screwed up earlier and was like, whoa, 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 whoa. My A can't be positive, because if it's positive, it's an upward facing cup. And what I've just drawn right here is a downward facing cup. And so it had better work out to be a negative number. And that's what we find that it does. If you do this experiment a million times and average it out, you'll get that number right there, regardless of how fast you start when you throw that thing or whatever. And that's because when you take calculus, you'll see this in an instant, that is the acceleration. And the acceleration, or it's 1/2 of the acceleration. The acceleration due to gravity is that, and that's how you determine what it is. Actually, you just do this experiment a bunch of times. And so, does this make sense what's going on here?
I think so.
Okay. And so this is the crux of the issue, and like, or the crux of projectile motion problems. With any projectile motion that we're going to be doing, we assume that the only force acting on this thing is the force of gravity. And you'll notice that I didn't start my watch back here when the person reached down and was throwing the ball, because there's two forces acting on the ball at the time. There's gravity, which is always acting on you. And then there's the force of the person's hand as they're moving it. Well, that screws everything up. And it gets so ridiculously complicated to actually do something like that. But once the instant that you let go of it, I'm not putting any force on it. It's the only force that's acting on this thing is gravity. And it turns out that force is equal to mass times acceleration. There. And since that's the case, since that's the only thing that's acting on it, it behaves in a very specific way. And when you take calculus, you'll be able to derive that directly from force equals mass times acceleration, and it's pretty cool. But for right now, we're going to say, forget all that. This is simply empirical. This is simply that you and I went out, we took a big old spotlight and a wall and a piece of paper and a stopwatch. And of course, we would have had to have used a ruler or a meter stick to find out the heights. But we did this experiment about 1,000 times. And we noticed, hey, every time you take these data points and you do this thing where you plug in the time and you get out the height and you take 3 of those points and go and solve, every single time we ended up with an A value that was very near minus 4.9. And we averaged all 1,000 of those trials that we did, and we found, yep, minus 4.9 always works. So that's what we're going to pretend we're doing right now. That we're going to say there must be some kind of law going on here. This must be some kind of truth about, I was going to say the universe, but some kind of truth about what happens when you throw things or when things are falling or moving on without any kind of force on them in Earth's gravitational field, that this always works out. So that's what we're going to take that as the ground truth. And we're going to say that whenever we are working with projectile motion problems, that this thing right here, that the function that describes the height as a function of time is given by this thing right here, where the A is equal to minus 4.9. So I'm just going to rewrite this where the A is minus 4.9. Minus 4.9 times t squared plus, I'm going to call this V0t, and I'm going to call this H0. Why do I call that H0? Well, let's plug in a 0 for t into this function, and let's see what we get. Well, when I plug in a 0, it's one of the nicest things you could do. The A term goes away, the B term goes away, and all that's left is the C term, which for some reason I'm calling H0. Why would you rename it from C and call it H0? Well, let's look at the graph of what we've done here. If we look back to our experiment, when time was equal to 0, the output was 1. Well, the 1, that was a meter, right? That was the initial height right there, right? So this says that when time was 0, right? I just plugged in a 0, that The height, right? Remember this F is just a record of the height of the ball. And I plug in a 0, the height was equal to 1. And we call that 0 right there. We put a little subscript 0 to just kind of tell us it's the initial height. When the experiment began, this was my initial height. And since it's height, we use H. And since it's the first height that we had when our experiment started, we call it 0. H0 is the initial height. So that's why that guy works. We have the tools to reason through why this thing is the initial velocity, which it is. That B term I've renamed to V0. But when you take calculus, it's so much more rigorous and so obvious when you take calculus why it has to be the initial velocity. For right now, we're just going to take that as just that. That's just God-given truth, like it's scripture. Like we were told this from on high, and we're just going to trust it for right now that this is the initial velocity of the thing.
Right.
Okay. And so in this case, it's positive because, and this is how we're going to think about this from now on. F gives me the height of the ball at any given time. If the velocity is positive, that means that it's moving in the upward direction. If the velocity were negative, that means that I would have started by throwing it downwards. It had an initial downward velocity. So the sign of that term, the V0 term, that is just basically says, are you going up or down? That's why the sign of the acceleration term is downward, because the force is pulling it downward. And that kind of makes sense with what we're doing right here is like, well, yeah, it's a downward facing cup, right? Like when you actually graph all this out, it's a downward facing cup. So that first thing has to be negative, but it also kind of makes sense when you start to interpret that as acceleration. It's like, well, in what direction is it accelerating? I don't know, take something and drop it, see what direction it accelerates. Oh, it starts going faster in that direction, in the negative direction. So it's going to start pulling you towards negative values, downwards, in other words. So, okay. The way that these problems are going to work in your homework. So this is the theory behind it, right? And this is what you're going to start with pretty much every single time. If you're given an initial velocity and you're given an initial height, well, then you know everything that there is to know about this function. And it's ultimately always going to look like this. And so let's do one. Let's look at this. So I'm going to get rid of this stuff right here. Okay. So which one did I want to do? Okay, so this is from page 418. Number 10. Very similar to a homework problem you're going to have. It says a rocket is fired upward. You'll notice it didn't say that a rocket moves in some parabolic trajectory. No, it's saying a rocket is just moving upward. Okay, it's fired upward. And then it says at the end of its burn. What now? Well, let's think about this. Back to our experiment. Somebody took an orange and threw it up, but we started our watch the second it left their hand. Why did we do that? Why didn't we start it when they were at the very bottom? Well, because we don't know physics well enough to be able to deal with that. The only thing we could do is when the only force acting on this thing is gravity. And so I'm not going to start my clock until it leaves the person's hand. Similarly, with this problem, it says at the end of its burn, that's the problem's way of telling you the rocket is no longer pushing on, or the fuel that's burning is no longer pushing the rocket upward. The rocket is now done, and it's as though that force that was pushing it up has let go. And so it's similar to the person who's thrown the thing that when it leaves their hand, now they're not acting on it anymore. That's what it's saying with the rocket. The rocket's being propelled, and then it is at the, it says at the end of its burn, means there's no more fuel, it's gone, and it's as though you had pushed it up with your hand and then you let go. And so, okay, this is how we pick together or pick apart these things. What I like to do with all of these is I draw a little picture. And so I'm going to think, okay, there's a rocket. This is my rocket. And it was burning, okay? And it was moving in the upward direction, and then it stopped. Okay, so I'm imagining, okay, there's some height. And if I had a wall and a spotlight and it shined its light, it would say that it was some height at the instant that we let go of it, or at the instant that the fuel burnt out. Okay, and it has an upward velocity. This is what it tells us. It has an upward velocity of 147 meters per second. So that means V0, the initial velocity of that thing, is 147 meters per second. Okay, and is 73.5 meters high. So at the instant that we could start doing physics on this thing, we call that time zero. And it says that that height is 73.5 meters high. So that means H0, the initial height, is 73.5 meters high. Now let's just, before we even go on with this, let's just imagine what's going to happen. This is the same thing as you've taken a ball and you've thrown it straight up. And this is the instant that time zero is when you've let it go. What's it going to do? Well, it's going to be, and now I'm going to make this an easier rocket to actually draw. We have our rocket. It's going to continue to move up because it's moving up fast, 147 meters per second at this instant. It is moving upwards. And so after, say, 1 second or whatever, it's going to be much higher, right? But then it's going to start slowing down and slowing down until it comes to a stop finally. And then it's going to start to drop, right? And it's going to start coming downwards. So first it's going to move upwards until its velocity reaches zero. Then it's going to start to move downwards like that. And what would we see if we were, again, keeping a record of what's going on? Well, at time zero, I'd put my dot right here. And then after some time goes by, it would come up a certain distance. And so I go over to some time value and it would be up. And then the next time step, it wouldn't be as high, it would start to crest. And so I could just imagine, oh, that's some kind of downward facing parabola like this, just like that. That is what I expect should happen. So this is kind of step one, where step one is identify, step one is graphic. Like this will help you. We're going to draw what it should look like. And all of these projectile motion ones are pretty much this right here. Okay, starts at 73.5. Since it has an upward velocity, it's going to reach some height. We're not sure what, but it'll turn back around after it stops burning out and then start falling to the ground. And this is what we should see if we were tracking data points as time went on. So now, let's go ahead and plug this stuff in right here. And we should find that the height at any given time is given by negative 4.9 t squared plus 147 t plus, because we're at a positive distance, plus 73.5. Okay, so let's see. Now remember what this is. F of t is it's the output of this function. So you give me any time. If I say, how high was it 1 second after you started your clock? You'd say, well, I'm going to plug in a 1, and you'd plug in a 1, and you do all this. And then that output, whatever it happens to be, would say that the height of that rocket at that point would be whatever your output is there when you plug in a 1 to F. That looks terrible, but that's an F of 1 right there. Remember, that represents the output you get when you do this calculation after plugging in a 1. Okay, so that's the picture. That's just the given information that they've given me. Now let's see what they're going to ask. Find its maximum height and when it is obtained. What's nice about having this picture is I could go, oh, they're asking about this point right here. They want to know the highest value that it gets. So that's what they want right there. They also want to know when, at what time, for what special time do I need to plug in? Yes, I'm putting a little asterisk after that. I call that T star. You'll see that a bunch if you go on in math. Like, kind of, that's like saying there's a special time. And we're going to say it's special because there's a star there. For what special time do I need to plug in to get what output right here? That's what we want to know. Well, that's a vertex, isn't it? Right? That's the idea with this. That's what's great about parabolas, is it's really easy to find the vertex. And we actually have like a real actual example of why we might want to. How high is it going to go? Ooh, I don't know, but I could tell you what time that's going to happen. What time is that going to happen? How do we find a vertex with this guy?
Gosh.
So don't think too hard about this. Watch this. How would you find what is the x value or the input value of the vertex of this guy?
Isn't it negative b over 2a?
Minus b over 2a is always where, in other words, for what input value the vertex occurs. Therefore, okay, where, for what value of t, what input value does this vertex occur?
Would you just use the numbers?
Exactly.
Okay,
So
so
the
minus
b, there's nothing special about calling it b. The only thing that was special about it was where it occurred in the function, right? Or like that it was the thing that went with the x term, and that the a is the thing that went with the squared term. And so this is exactly in the form at squared plus bt plus c. We just need to identify what the a and the b are. And so where is this vertex value? This special value of t occurs where?
At 147 minus, or I guess minus 147.
Minus 147, there you go.
Over minus 4.9.
Over what?
Is that a 4.9?
That's a minus 4.9, but
oh yeah, 2 times that.
There you go, 2 times minus 4.9. Okay, actually, we'll do this real quick just to make this complete, because now, okay, they're giving us actual applied problems, and they're not in exact. These aren't like square roots and stuff like that. They're giving us, 4.9 and 73.5. So I'm going to use a calculator, and do that. First off, a minus and a minus, the answer is going to be positive. So I'm not going to worry about that. I'm going to say, okay, 147 divided by 2 divided by 4.9. Oh, look at that. I think I get a 15. Let's make sure. 147 divided by 9.8. There we go. Okay, so that's actually not that bad. So, okay, that is the time that it occurs. So in other words, after the rocket burnout, let's think back to what this graph means. The rocket was burning, blah, 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 and then it burnt out, so we started our clock. The clock started, and it was at 73.5. So we watched it, and we watched it, and we watched it, and after 15 seconds, then the rocket stopped moving, and we want to know what height was it? How do we find the height? Given that we know the input value of t, how do we find the height? How did you do it in your homework?
You found this. What was it? Found this? No, that was for the X. Hold on.
Or let's not think about homework. Let's think about this. You have an input-output relationship, right?
You plug in the input.
Plug in the input, right? And this is what I like about this picture here, is I think at least it takes a lot of the guesswork out for me. Because if I didn't have this picture here, I would be thinking, okay, now I've I've solved this. Okay, I plugged that in and I got this. Now what do I do? I'm not sure, but what I could do here is think, the question is saying, what is the maximum height? In other words, how high did this go right here? But remember what this is. The outputs, and I've written them here, they are the outputs of this function right there. So if you know the input, you could find the output. Similarly, if you know the output, you could solve for inputs as well. And so we got to keep in mind that we're dealing with functions, and that the input-output relationship is almost always going to come into play whenever you're given a word problem. And that's why I like to draw this, because at least to me, it takes the guesswork out. It's like, wait a minute, I need to know how high that is. Well, that's a function. If I need to know what that is, and I know what that is, I'm done. I just take that number and plug it in, and it gives me the output. So let's do that. We know that when I plug in a 15, we're at the highest point. So f of 15 is equal to minus 4.9, 15 squared, plus 147 times 15, plus 73.5. And I'm not going to do that on my crappy little calculator. I'm actually going to do that real quick on Wolfram Alpha. Give me a second. So we have minus 4.9 times 15 squared plus 147 times 15 plus 73.5. And I get that when I plug in a 15, I get out 1109.5. And so then when my input is 15, my output is 1109.5. And I could tell the way I've done all this, the way I've set everything up, and even the way that I found 15, that has to be the vertex right there. It also makes sense too, because that number is bigger than 73.5. Okay, nice. I can figure that it should be bigger. Okay, the last question here is, when does it reach the ground? So they're saying, right, they want to know when does it reach the ground. They're basically saying solve for t, right? That's what we're trying to find. And remember, anytime we're working with functions, we're talking about an input-output relationship. And so they're saying when, well, that means time, right? So they're basically saying solve for t. When means, in this case, solve for t. But solve for t such that what? Well, we input-output relationship. They're saying find the input when the output is what? What does it mean to reach the ground in this context?
Hit 0 again.
There we go, right? They're basically saying when the height is 0, find out when the height is 0. And so that's usually how this kind of thing goes, right? And let's look at what we did here. First off, they said, when does it reach its max? Well, what now? Well, in this case, since it's a parabola, we could actually find that point right there. We know the input values of a vertex. We know how to find a vertex. So that's how we could find that. And so, okay, we got an input value. Cool. But they want to know, well, how high is that? Well, that's an output value, right? Now we have an input value. We could take that, plug it in, and get an output value. So that's a special one. When they ask, like, when does something reach its maximum or its minimum, that's a new kind of thing. It's not so easy to figure out. That's kind of, that's the conceptual leap here, is that we have some kind of object that has a certain shape that we know about. Like, we know where this shape ends up right here because of certain properties of parabolas. But then the rest of this is really, it all comes back to input output. The rest of the questions that they could ask are just like input output questions. They're saying, okay, well, if we know when the max occurs, how can we find out what the value is? Well, you have an input value. So you could find an output value by plugging in the input value. Now they're doing the reverse of that. They're saying, here's an output value, and we had to kind of translate that. When will it reach the ground? Well, what does it mean to reach the ground? Well, it means that the output value is 0. And so the output value is 0. And now we could say, well, I could kind of see what that's going to look like here. In fact, I expect that since this thing is a parabola, we're going to have 2 possible values. And of course, that's going to be the case with the parabola, that there's 2 possibilities. One of them should be negative. And I could see that from this graph. Another reason, okay. That's another reason why I like to graph things, because as we start working, no, you can't have that. As we start working these problems out, this is going to confirm for me what I'm about to see. Like, I could see, okay, it's asking me for when the output value is 0. So that's what that means. When does it hit the ground? Wait, when? Okay, so they're asking for a time. Hit the ground means the height is 0. Set the height, or the output, equal to 0 and find the time. And then I'm going to go use my drawing here, my graph, to kind of wrap my head around what I'm about to see. And I can see that this thing is a parabola, and it's going to extend back into negative time. So when I go to solve this thing for 0, I should end up with 2 answers. One of them should be negative. So that's what I'm expecting right now. So, okay, let's do that real quick, finish up. So we have that written down, there. So we're going to say, when does it hit the ground? In other words, find the t values when the height is equal to 0. Well, this thing is the height. And that's what we're trying to solve right now. If they said, at what time will it reach 20 meters above the ground? We could say, well, hold on. When is it going to be 20 meters? The output is asking, when is the output of this function equal to 20? And instead of writing a 0, I would say, when is the output of the function equal to 20? I would set 20 equal to this and solve. That's not what it's asking, but you're going to have ones that are like that. And when you do that, you would still, and I can just see from my drawing here, that I should also end up with a positive and a negative answer. If they ask me, when will the rocket hit 1,000 meters above the ground, I could see, ooh, look at that. 1,000 is between here and there. And so I could imagine that, we should get two answers. One of them here and one of them here. And that actually means that if you think about it, right, the rocket's going up and then it's going to hit 1,000 and go a bit above that and then come back down to 1,000 at another time. And so we would have two valid times that we'd want. So I'm telling you, having this picture will take a lot of the guesswork out of it. Whereas if you just have it in your head, I just set it to whatever and solve for whatever, and then I'll throw away the negative answer, or I'll throw away the smaller answer. Well, you might not want to throw away the smaller answer. But I think that having the picture will help keep all of that in context. So long story short, we are trying to solve this right here because we want to know when, for what times, is the output of that, or the height of the rocket, equal to 0. And so we have 0 equals negative 4.9t squared plus 147t plus 73.5. No way in hell you're going to factor that guy. So, and trying to complete the square would be way too much work. So let's just use our best friend, the quadratic formula. So, x equals negative b over 2a. Oh, hey, we already did that. We already know that negative b over 2a is 15. That's nice. That'll help us. B squared minus 4ac all over 2a. This will be a positive 15 plus or minus. I'm going to go ahead and do this in Wolfram. Do it to it. That's right, buddy. So let me do this. The square root of 147 squared, 147 squared minus 4 times a, which is minus 4.9, times c, which is 73.5. Square root of that divided by 2 times a is negative 4.9. And I get negative 15.4919. This makes me feel really good, actually, because I could see that the majority of the time, it's not going to take that long before that happens. So that shouldn't be a very big number. 15 minus that would be minus 4.9. Okay, so that makes sense. But we don't care about the negative answer in this case because we don't want a negative answer. So the 15 plus the 15 should give me 30.4919 seconds. That should be it right there. And so we'd say that when it hits the ground again is after 30.4919 seconds. And I'm going to make sure I got that right by plugging this in real quick. So yep, 30.4919 right there. The negative one does not make sense because, well, none of this applied beforehand. He was like in the process of being thrown, right? And it's not doing this thing. You can't say that when did the rocket take off? Well, we don't know because this only applies during the free fall. Right? We can only start this analysis once the free fall occurred, which is when the rocket burned out and why we chose to start that. A really good question here would be something like, when does the rocket equal, or when does the rocket reach 1,000 feet? And sometimes those questions come up like, when is the first time it reaches 1,000 feet? Or when is the second time it reaches 1,000 feet? Or like, how many times will it reach 1,000 feet? Describe those times. And you could see that by graphing it, that makes a lot of sense, because we're saying that the height is equal to 1,000, and then they're asking when. So in other words, they're saying find a time. And I could see just by the graph here that that actually makes sense, right? That we're going to get 2 positive times right there. And that, again, just to be really clear here, would be what we would get if we said, well, when the output is 1,000, what is the input? That's the same thing as saying when the output 1,000 is equal to this thing right here, and then solving for t. And you'll notice we're not quite in the form that we could use. I'm sorry, I erased all that. I'm not sure if you were done. I could put that back up if you'd like. But right now, what do? Well, we know how to solve things that are equal to 0. This isn't equal to 0, but we can make this equal to 0 pretty easily. Just subtract 1,000 from both sides. And then we'd have 0 equals minus 4.9t squared plus 147t. 73.5 minus 1,000. 73.5 minus 1,000 is negative 926.5. And that's how we would do that. And we'd say, well, I know how to deal with that. That's negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. And then we're just taking each one of those, treating that as an a, treating that as a b, treating that as a c, and using it to solve for t right there. So that's the idea with how we could use all of this machinery that we've been developing so far to answer questions like this and actually apply them to stuff.
Okay.
You good with this? Does this make sense, what we're doing?
I think so.
Okay, good. So again, if you have questions, let me know. But this input-output thing is always going to be part of it. And if you could identify, it's like, what are they asking me for? Oh, they're asking me for an output. Like in this case, they're asking me for a height. That means that if I know a time, if I know an input, I could find an output. Or if they're asking for when does the max or min of something occur, they're asking about the vertex. Remember the homework. You could find a vertex by, if it's like this, because you know that nifty little formula, negative b over 2a, and you could find the input value. How do you find the output value? You just take the input value and plug it out. Again, input-output relationship. You want to know, where does this thing equal 1,000? Well, when the output is 1,000, then you just set that guy like that, and you say, I don't know how to solve something like that. Yeah, but you know how to solve it when it's equal to 0. So turn this thing that you haven't seen before into a thing you've seen before and solve for t. And that's the idea. Okay, man. So, you ready for your homework?
Yeah.
All right. This is chapter 9, section 8, pages 418 through 19. And we're going to do numbers 1, 5, 7, 9. And yeah. this damn thing. 11 and 13, and I have something to say about 13. Okay, 13 number or letter C, it has parts A, B, and C. The way I hate the way they say this. Say when it says when it falls to earth. And I'm like, this is again, it's a rocket and stuff like that. And they're asking when it falls to earth. What I think they mean by that is when it starts to fall to earth. And so if we're thinking about this as a rocket that went up, it started, it went up, and then it stopped, and then it came back down in the downward direction. What are they saying? Well, when it fell to earth, I think they're meaning when it begins its fall. And so what I think they mean there is like, when does it stop going up and start coming down? In other words, they're asking you to find the vertex, I think.